So, computers really have allowed us to do some pretty amazing things. Think global telecommunications, international commerce, global transportation, breakthroughs in medicine, distributed education, online shopping, online dating, and just the internet in general. Computers are allowing us to explore our own world and other worlds, and of course, some seemingly mundane things like permitting us to spy on our pets from work or communicating with our friends in a nearly indecipherable stream of emoji. But don't call computers magical. They are not. I repeat, are not magical. So before we get into what we're going to talk about in this series, it might be useful to tell you what we are not going to talk about. We aren't going to teach you how to program. Programming is a really crucial aspect of computer science, and we will get to the rules that guide the logic of hardware and software design. But we aren't going to teach you how to program an Arduino to water your plant, or how to change the CSS on your grandma's sewing blog so visitors' cursors turn into kittens. This also isn't a computing course, or at least how computing is thought of in the US. Computing here is a goal. It's what computers do, and we'll talk about some of that for sure. But our goal for this course is much broader. But computing means other things in other countries. It's all pretty confusing. But what we are going to look at are the history of computers, even before we had electricity. We're going to retrace the design decisions that have given us our present-day components. We're going to talk about how operating systems work, or don't work, how the YouTubes get to you over the internet, how our smartphones and other smart devices are, well, getting smarter, and of course, mysterious futuristic stuff like quantum computing and frustrating present-day stuff like hacking. But what if we want to use computers not just to fetch and display data, but to actually make decisions about data? This is the essence of machine learning, algorithms that give computers the ability to learn from data and then make predictions and decisions. Computer programs with this ability are extremely useful in answering questions like, is this email spam? Does a person's heart have arrhythmia? Or what video should YouTube recommend after this one? While useful, we probably wouldn't describe these programs as intelligent in the same way we think of human intelligence. So even though the terms are often interchanged, most computer scientists would say that machine learning is a set of techniques that sits inside the even more ambitious goal of artificial intelligence, or AI for short. In order to train our machine learning classifier to make good predictions, we're going to need training data. To get that, we'd send an entomologist out into a forest to collect data for both lunar and emperor moths. These experts can recognise different moths, so they not only record the feature values, but also label that data with the actual moth species. This is called labelled data. Because we only have two features, it's easy to visualise this data in a scatter plot. Here I've plotted data for 100 emperor moths in red and 100 lunar moths in blue. We can see that the species make two groupings, but there's some overlap in the middle, so it's not entirely obvious how to best separate the two. That's what machine learning algorithms do, find optimal separations. A couple of years ago, Google and Facebook demonstrated deep neural nets that could find faces in photos as well as humans, and humans are really good at this. It was a huge milestone. Now deep neural nets are driving cars, translating human speech, diagnosing medical conditions, and much more. These algorithms are very sophisticated, but it's less clear if they should be described as intelligent. They can really only do one thing, like classify moths, find faces, or translate languages. This type of AI is called weak AI or narrow AI. It's only intelligent at specific tasks. But that doesn't mean it's not useful. I mean, medical devices that can make diagnoses and cars that can drive themselves are amazing. Truly general purpose AI, one as smart and well-rounded as a human, is called strong AI. No one has demonstrated anything close to human-level artificial intelligence yet. Some argue it's impossible, but many people point to the explosion of digitized knowledge like Wikipedia articles, web pages and YouTube videos as the perfect kindling for strong AI. Although you can only watch a maximum of 24 hours of YouTube a day, a computer can watch millions of hours. For example, IBM's Watson consults and synthesizes information from 200 million pages of content, including the full text of Wikipedia. While not a strong AI, Watson is pretty smart, and it crushed its human competition in Jeopardy way back in 2011. What will be interesting to see is if these types of learning techniques can be applied more broadly to create human-like strong AIs that learn much like how kids learn, but at super accelerated rates. If that happens, there are some pretty big changes in store for humanity. Your computer is connected to a large distributed network called the internet. I know this because you're watching a YouTube video which is being streamed over that very internet. It's arranged as an ever-enlarging web of interconnected devices. For your computer to get this video, the first connection is to your local area network, or LAN, which might be every device in your house that's connected to your Wi-Fi router. This then connects to a wide area network, or WAN, which is likely to be a router run by your internet service provider, or ISP, companies like Comcast, AT&T or Verizon. At first, this will be a regional router, like one for your neighbourhood, and then that router connects to an even bigger WAN, maybe one for your whole city or town. When your computer wants to make a connection to a website, you need two things: an IP address and a port, like port 80 at 172.217.7.238. This example is the IP address and port for the Google web server. In fact, you can enter this into your browser's address bar like so, and you'll end up on the Google homepage. This gets you to the right destination, but remembering that long string of digits would be really annoying. It's much easier to remember google.com. So the internet has a special service that maps these domain names to addresses. It's like the phone book for the internet, and it's called the Domain Name System, or DNS for short. You can probably guess how it works. When you type something like youtube.com into your web browser, it goes and asks a DNS server, usually one provided by your ISP, to look up the address. DNS consults its huge registry and replies with the address, if one exists. In fact, if you try mashing your keyboard, adding .com and then hit enter in your browser, you'll likely be presented with an error that says DNS failed. That's because the site doesn't exist, so DNS couldn't give your browser an address. But if DNS returns a valid address, which it should for youtube.com, then your browser shoots off a request over TCP for the website's data. There's over 300 million registered domain names, so to make our DNS look up a little bit more manageable, it's not stored as one gigantically long list, but rather in a tree data structure. What are called top-level domains, or TLDs, are at the very top. These are huge categories like .com and .gov. Then there are lower level domains that sit below that, called second level domains. Examples under .com include google.com and dftba.com. Then there are even lower level domains called subdomains, like images.google.com and store.dftba.com. And this tree is absolutely huge. Like I said, more than 300 million domain names, and that's just second level domain names, not all the subdomains. For this reason, the data is distributed across many DNS servers, which are authorities for different ends. Over the last 3 episodes, we've talked about how computers have become interconnected, allowing us to communicate near instantly across the globe. But not everyone who uses these networks is going to play by the rules or have our best interests at heart. Just as how we have physical security like locks, fences and police officers to minimise crime in the real world, we need cybersecurity to minimise crime and harm in the virtual world. Computers don't have ethics. Give them a formally specified problem and they'll happily pump out an answer at lightning speed. Running code that takes down a hospital's computer systems is no different to a computer than code that keeps a patient's heart beating. The scope of cybersecurity evolves as fast as the capabilities of computing, but we can think of it as a set of techniques to protect the secrecy, integrity and availability of computer systems and data against threats. Let's unpack those 3 goals. Secrecy, or confidentiality, means that only authorised people should be able to access or read specific computer systems and data. Data breaches, where hackers reveal people's credit card information, is an attack on secrecy. Integrity means that only authorised people should have the ability to use or modify systems and data. Hackers who learn your password and send emails masquerading as you is an integrity attack. And availability means that authorised people should always have access to their systems and data. Think of denial of service attacks, where hackers overload a website with fake requests to make it slow or unreachable for others. That's attacking the service's availability. To achieve these 3 goals, security experts start with a specification of who your enemy is, at an abstract level called a threat model. This profiles attackers, their capabilities, goals, and probable means of attack, what's called, awesomely enough, an attack vector. Threat models let you prepare against specific threats, rather than being overwhelmed by all the ways hackers could get to your systems and data. And there are many, many ways. Given threat models, security architects need to come up with a solution that keeps the system secure, as long as certain assumptions are met, like no one reveals their password to the attacker. There are many methods for protecting computer systems, networks, and data. A lot of security boils down to 2 questions. Who are you, and what should you have access to? Clearly, access should be given to the right people, but refused to the wrong people. So to differentiate between right and wrong people, we use authentication, the process by which a computer understands who it's interacting with. Generally, there are 3 types, each with their own pros and cons. What you know, what you have, and what you are. What you know authentication is based on knowledge of a secret that should be known only to the real user and the computer. For example, a username and password. This is the most widely used today because it's the easiest to implement. But it can be compromised if hackers guess or otherwise come to know your secret. Some passwords are easy for humans to figure out, like 123456 or QWERTY. But there are also ones that are easy for computers. Consider the pin 2580. This seems pretty difficult to guess, and it is for a human, but there are only 10,000 possible combinations of 4-digit pins. A computer can try entering 0000, then try 0001, and then 0002, all the way up to 9999 in a fraction of a second. This is called a brute force attack because it just tries everything. There's nothing clever to the algorithm. What you have authentication, on the other hand, is based on possession of a secret token that only the real user has. An example is a physical key and lock. You can only unlock the door if you have the key. This escapes this problem of being guessable, and they typically require physical presence, so it's much harder for remote attackers to gain access. Someone in another country can't gain access to your front door in Florida without getting to Florida first. But what you have authentication can be compromised if an attacker is physically close. Keys can be copied, smartphones stolen, and locks picked. Finally, what you are authentication is based on you. You authenticate by presenting yourself to the computer. Biometric authenticators like fingerprint readers and iris scanners are classic examples. These can be very secure, but the best technologies are still quite expensive. Biometric authentication, however, is probabilistic. There's some chance the system won't recognize you. Maybe you're wearing a hat or the lighting is bad. Worse, there's some chance the system will recognise the wrong person as you, like your evil twin. Of course, in production systems, these chances are low, but not zero. Another issue with biometric authentication is it can't be reset. You only have so many fingers, so what happens if an attacker compromises your fingerprint data? This could be a big problem for life, and recently researchers showed it's possible to forge your iris just by capturing a photo of you, so that's not promising either. Basically, all forms of authentication have strengths and weaknesses, and all can be compromised in one way or another. So security experts suggest using 2 or more forms of authentication for important accounts. This is known as two-factor or multi-factor authentication. An attacker may be able to guess your password or steal your phone, but it's much harder to do both. Make your password stronger, turn on two-factor authentication, and never click links in unsolicited emails.
We have now data science, and of course with data science, we need to differentiate now what is data and what is information. Technically, when we say information, we deal with processed data. So when we say data now, we're dealing with elements that is raw and meaningless to the user. So if it's raw and meaningless, we have to process this in a form called algorithm in order to provide or squeeze up the juice, which is called information. So it's the processing that comes in the way. So technically, data science is all about processing. And of course, the process is analysis. Okay, so moving forward, we have now what we call data science. So let's have a concrete definition now. So the textbook or the theoretical academic definition of data science is an interdisciplinary field that uses scientific methods, processes, as I've mentioned, algorithms and systems to extract knowledge and insight from noisy, structured and unstructured data. So technically, data is noisy, unstructured or unstructured. And of course, apply knowledge and actionable insights from data across a broad knowledge of application domains. Okay, so there are 5 stages of data science. So technically, we have big data. Okay, so what am I going to do with this? So which are the ones do I need and which are the ones I don't? So technically first, you set your target. What is the data that I want? If I have identified that, I'm going to capture, maintain, process, communicate, and analyze. So technically, what I want may be in the form of hula or a scientific guess or hypothesis. That is what I want. But technically, once you process your data, it may come up after doing the 5 steps. It may come up the other way. So we just have to wait what these 5 steps will be coming up afterward.